Hey everyone, hope you guys and gals are doing great today. We're going to be in our workbooks, lesson number 7, as you see right there, 58 to 67. So I know some of you are choosing to go and work on the workbooks on your own. That's great. Some of you want to go through with me, and that's just A-okay as well. So let's take a look here. So we're going to start on page 58. Go ahead, let's read that first paragraph about Felicia, and she's tracking some snowfall, and then we'll pick up from there. Okay, so hopefully you've read that in your book. If not, pause this and come back. But it says in the table, 0 represents the time when the storm started. How much snow was on the ground then? Well, it tells us, hey, there was already snow on the ground from a previous storm. So we can actually answer this question. We know that right now, without a doubt, there are 2 inches, right, of snow on the ground. How much snow fell in the first hour? Well, the snowfall is consistent from hour to hour, right? It said every hour, exactly 1.5 inches, right, of snowfall each hour. And feel free, if you want to pause this and answer some questions and see how you did, do that. If you just want to listen to me and jot down whatever I'm jotting down, that works too. So we know there was 2 inches on the ground. We know 1.5 inches of snow falls every hour. So how much snow fell at the first hour? Well, again, it's not just that 1.5 inches, right? It's really that 1.5 inches plus what we started with, right? So it's really that 1.5 inches, right? And then I've got to add the 2 inches that I started with. So at the end of the first hour, I actually have 3.5 inches of snow. All right. How can we use addition to find the amount of snow on the ground at the end of each hour? Complete the table. Well, I think we can use this right here, right? And if you're thinking ahead a little bit, this is our rate of change, right? This is what's changing the amount of snow on the ground. So 3.5, right, should go right here. Oops, just covered up my decimal point. There we go. So 3.5 goes here. All right, and again, that's the 2, right? We added that 1.5 inches. Well, the same thing's going to happen from hour 1 to hour 2. Again, I'm getting another 1.5 inches. So 3.5 plus 1.5, now I'm up to 5. Right, same thing from hour 2 to hour 3, I get another 1.5 inches of snow. Now I'm up to 6.5. Same thing for the next 2 hours as well. Again, it keeps going up by 1.5 inches. So now I'm up to 8. And at the end of hour number 5, we have 9.5 inches of snow. All right. So describe how we can use addition. Just simply what I did, right? I'll just say keep adding 1.5, right, to the previous total, right, or the end of that hour. Again, that is repeated addition. Right, repeated addition is the same thing as multiplying. So I think we could multiply as well. It says suppose you multiply each hour in the table by that 1.5. Again, that's our rate of change, which is the exact same thing as slope. Well, if we multiply by 1.5, so in other words, like, hey, let's say I start at hour 6, right? Let's say there was a hypothetical 6 that's up here. And our table continued to go on. If I multiply 6 by my 1.5 inches of snow that I know I get every hour, right? That turns into 9. But remember, 9 is not what goes in here, because look, I have to have more than 9.5. Remember, you have to then add back, right? That 2, that's what we started with. So really we'd put 11, all right, in here. And while we're talking about it, guys, this, let me zoom out a little bit. So when we have this table, we have a special name, all right, for 2. All right, this is our initial value, right? Because at time 0, we already had 2 inches of snow. That's what we started with, right? That's your initial value. That's your starting point. That's something new, right? Last year in 7th grade, we didn't have that. We didn't have initial values. We just had 0. We didn't have, hey, at time 0, you're already starting with something. Anyway, before I get off track, let's keep going here. Suppose you multiply each hour by 1.5. What else do you have to do, right? I'll just say on here, add 2 inches, which is the initial value. All right, so let's make sure we do that. Yes, we can write an equation for this, right? S in our equation right here, this is the amount of snowfall. So snowfall is equal to, well, what did we start with? 2. And how much snow do we get every hour? 1.5. So you could say S equals 2 plus 1.5H. You could flip-flop those around if you like and say 1.5H plus 2. They mean the same thing. Okay. Here we go. So proportional relationships, gang. If you think about proportional relationships, and I hinted about this just a little bit ago, proportional relationships in 7th grade, if you were a graph, you did 2 things, right? If you, oh no, that's not a 7th grade proportional relationship, but that one is. So if you were that graph last year and I said, is that proportional, you would say absolutely, right? Because it does the 2 things you have to do. It's got to be a straight line. Yep, sure is. And it's got to go through the origin. Well, this year's graph look like this, right? They look different, all right? They look different because they don't start at the origin, right? Down here, this is the origin. My graph doesn't start there. It starts all the way up here, and that's that initial value I was talking about. So there's the biggest difference in our graphs that we're going to see now. We aren't going to have our graphs going through the origin, which doesn't have an initial value. Well, it does, it's just 0, right? We actually get an initial value now. So our goal today is going to be start to identify initial value, as well as rate of change or slope. Okay, so this is just our table, guys, that's been graphed. Okay, that's all. Again, slope of that line, 1.5. All right. Let's look down here about Dora. Let's see, she's opening a savings account. Good for her. And, all right, she deposits $50. She gets her paycheck. She puts $25 into it. Describe the initial value and rate of change, all right, for this scenario. So the initial value, that's again, what is she going to start out with? So the initial value in this case is $50, right? What's her rate of change? Well, what's changing how much money goes into her account? Well, every paycheck, $25 goes into her bank account. So the rate of change is $25, right? This is the amount that she adds, right, for each paycheck amount. She adds each paycheck. Cool. Okay. All right. Again, if you need to pause it and read this problem, you can. We're going to be talking about 2 different kind of maple trees. We got a silver maple tree, and we see the graph for that one right here. Whoa. All right. Then we also have the red maple tree. All right, so here's silver here. The red one, it doesn't really give us anything. It just tells us about this right here. It says, hey, had a starting diameter of 4 inches. Hint, hint, starting diameter of 4 inches. Diameter grew at an average rate of 0.3 inches per year. Okay, so again, think initial value, right? When I think initial value, I think 4 should be the initial value. Again, this is for the red maple tree. Our silver maple tree, if you look over on our graph here, where's the initial value? Right, one of those green circles is the initial value. Yep, it's this one right here. Okay, we went ahead and they're so nice. They've made a table for us for our red maple tree. Again, this is the red maple tree, and then they went ahead and graphed it. Okay, so now I can look at this graph and compare it with this graph, and sometimes that's a good choice. Guys, if you're confused or you're not sure, hey, I've got a table and a graph, we'll either make tables out of both of them or make graphs out of both of them, because sometimes it's easier to compare graphs or tables when they look alike. So, and our question is, which one of these functions has a greater rate of change? So in other words, which one of these trees is growing more each year? Okay. Well, I can't just look and say, hey, at the end of year 4, the red maple tree has grown, this much, that number there, 5, maybe, and then go over here and look at this one and say, okay, hey, that looks like it's pretty close as well. You know what I mean? Like that's got to be, somewhere between 4 and 6 too. So that doesn't help me. What I need to do is figure out slope for these two. So if you guys want to pause this and try that, you can. If not, we're gonna make that calculation here in just a second. You know what? Actually, we're gonna do that now because the other page. Yeah, let's do that now. So here's what I would do, guys. Let's look at the silver maple tree first, and let's figure out slope for this one. So pick some ordered pairs that we like. Okay, I like this ordered pair right here. Right, this is 0, 0, 3. I like this one. That's the ordered pair 2, 4. Okay. Now I'm good to go. Y2 minus Y1, X2 minus X1. Right, 4 minus 3 over 2 minus 0. That's 1 over 2. Okay, so this has a slope of 1/2, or a rate of change of 1/2. If you'd like that as a decimal, that's not bad. We can make that one work. 0.5. Cool. All right, so there's silver maple tree is 1/2, or just 0.5. Let's find some good points for this one. I'm not crazy about any of these, right? Because I don't have any good numbers here. But what I can do, guys, is look right here and take some of these. So I'm going to use 0 and 4, and I'm going to use 1 and 4.3. Okay, sounds good. So again, y2 minus y1, 4.3 minus 4. X2 minus x1, 1 minus 0. This turns out to be 0.3 over 1. What's anything divided by 1? Well, just that thing, right? So this just turns out to be 0.3. All right, again, this is the red maple tree. So here's our rate of change for both of these. So here's red, here's silver, and now we can figure out, okay, which one's growing at a quicker rate of change. All right, I'll let you figure that out. Okay, so now we can start to answer some questions here. And it says, write ordered pairs for the points that show the initial value on each graph. Right, well, the initial values, we could go back and look at our graph there, but the silver maple was 0.3, right? 0.3. The red maple was 0.4. What do you think the initial value represents? Well, that's the diameter of the tree when they started this, study. When study began. Okay, I don't like the way this is worded. Right? It just says fill in the blanks to describe the rate of change. Guys, the rate of change is just slope, right? That's what we solved for right over here. Okay, so don't worry about question number 3. What do the rates of change represent? Well, again, in the context of the problem, the rate of change just represents the growth of each tree per year, right? That's the most important part of that, right? Each year that tree grows a half an inch. Each year the other one grows 3/10 of an inch. So which one has a greater rate of change? I think we finally figured this one out, right? The silver maple does. What does that mean? Well, that just means it grows faster than the red maple, right? It grows faster, all right, than the red maple tree. Super. Okay. Your turn, guys. Here I got a table and a graph. Shows how much money a store sells earning T-shirts and team caps. So here's our T-shirt, right? Here's our caps. Compare the rate of change for the two functions. So if you guys are feeling up to it, pause the video, figure out rate of change. When you come back, bam, like magic, I'm going to have calculated rate of change with you, and then we can compare them, okay? Okay, welcome back. Bam, here it is. I told you I'd have everything written down for you. So I figured out slope or rate of change. On T-shirts, I came up with 4. On caps, I came up with 2. So what does all that mean, though? That means the rate of change for T-shirts is $4. The rate of change for T-shirts is $2, right? Or the rate of change for T-shirts is double what it is for caps, all right? Okay, sounds good. Onward we go. A few more, and then you guys will be able to work on some of these on your own. Again, here's our scenario here. We've got Mrs. White, Mr. Brown. They each buy a used car for, let's see, Miss White buys hers for $3,000, and she makes monthly payments of this. Think to yourself, initial value, rate of change, which is which? Mr. Brown also buys a used car. His monthly payment plan is shown in the table. Again, I want you to think about initial value, rate of change. Right? Initial value, rate of change. Right? For Mr. Brown's, I've got a nice table here. Right? This nice table here. I don't have anything for Mrs. White other than the fact that, hey, the car was $3,000, initial value. She makes payments of $300 on it. So what they've done, they've taken all of this info and they have already created a nice table for us here. Again, in our table, when we are at time 0, right here, whatever the other value is, 2,400, 3,000, that's your initial value, right? When your x value is 0, the other number, the y value, that's your initial value. So again, start to see that. Then, right, our workbook, as nice as it is, has even gone one step further, and now it's graphed these two lines for us. Again, these lines look very similar. All right, very similar. Mr. Brown, green one, Miss White, the black one. All right. I see negative slope, all right, on both of these. These lines look to have a certain relationship between these lines. Let's come back to these again. You in your workbook, you can flip back and forth. I'm not going to do that. But look at the tables on the previous page. How much does Mr. Brown's amount go down by each month is what it's asking for. It decreases. Well, again, it's going down. The problem told us it's going down $300. All right, $300. What about Mrs. White? Well, same thing, right? Going down $300. How does our answer, right, in number 7 tell us about rates of change? Well, again, these, right, both of these are the rates of change, right? These are their slopes. So I would say the rate of change is the same. Yay. What does the graph show, or how does the graph show this? Well, this is the cool part. Both lines, right, have the same slope. And this is where we get that special kind of line. So go back, guys. Look on 62. Look at the green and the black line. Do you think those two lines will ever run into each other? Do you think those lines will ever intersect? No. Why not? Because they are parallel to each other. So parallel lines have the same slope. Cool. All right, what's the initial value for each function? And what do the initial values mean in the context of the problem? Well, the initial value is how much they bought the car for, right? So I already gave this one a little bit away. So our initial values, we had, I think, what, 2,400 and 3,000. Right, so this is amount I didn't buy it. We purchased the car for. Okay. Fill in the blanks to write an equation for each function where x is the number of months and y is the amount owed. So in other words, if I want to figure out how much I owe, we're gonna say is represented by the letter y. Well, in Mrs. White, again, they both have the same slope or the same rate of change, 300. But in this case, right, our amount is decreasing. So Mrs. White, she bought her car for $3,000. And then it decreases. So if I want to figure out, hey, after 1 month, how much do you owe? Well, you had 3,000. We'd subtract 300 from it, right? So 300 times x, right? X is the number of months that we want to figure out, right? After 2 months, well, it's 300 times 2, 600. We subtract 600 from 3,000, right? Now she owes $2,400. All right, Mr. Brown, same thing, right? Initial value, 2,400. Right, same rate of change, 300x. Well, because they both have the same rate of change, it kind of leads into question 11. Does it take them the same time to finish paying for their cars? I mean, they're paying the same amount on them, so shouldn't that be the same amount of time? No, not at all. Why not? All right. Well, first off, does it take the same time? No. Why not? Even though they pay the same amount each month, they didn't start with the same number, right? I'll just say on here, the cars were 2 different prices. Okay? If they're both the same price, then yes, of course they would be. Okay. Okay, here we go. Textbooks rentals. Below are 2 companies who rent textbooks. So like, hey, I want to rent a textbook for 2 months or 6 months or 4 months, whatever it is. What's the initial value for each function? and then it wants to know the cost to rent a textbook for 4 months. So guys, pause this. You guys go ahead and give it a shot. Again, what's the initial value, right? And then, hey, I rent it for 4 months. How much do we cost? So go ahead and pause it, and then we'll come back. Okay, welcome back. Here you go. So here's our initial values. I'm assuming you guys all would have done well on Company A with an initial value of 15. And it's really, I put a circle around it, it's really this 15 here, right? It's not the 15 that has M, because that's talking about our rate of change. I didn't have an initial value for Company B, right? Because it's just, hey, you just pay $19 per month. There's no, like, other fees or anything else that you would pay. So no initial value there. To figure out how much we pay when we rent a textbook for 4 months, we just plug in what that monthly fee is, multiply it by 4. So in Company B, very straightforward, right? I just take 19, multiply that by 4, I got $76. Company A, a little bit different, right? Company A, I've got to take $15, which is their monthly fee, times 4 months. Right, we see that right here. All right, then I've got to add 15 to that. So that ends up being $75. So again, just a problem there to get you thinking about that. Okay, so these 2 pages, gang, you guys are on your own now. I leave you to work through these. All right, so work through those 1, 2, 3 problems. All right, and then as always, here's our homework for these, and I do like all of the questions, so we're going to work on both of those. Okay. As always, any questions, let me know. This will be your homework, so finish up with this, and don't rush through it. Do a good job. If you got questions, raise your hand in the air. All right. Have a great day.